Hi guys, welcome to this tutorial on linear regression from scratch in Python. Let's start by touching the basics of ML first. Machine learning specifically. So in machine learning, we have different kinds of algorithms. Okay, we broadly categorize all these algorithms in these three categories. So first one are the supervised algorithms, the supervised ones. Other ones are unsupervised ones. Okay, and third ones are the reinforcement machine learning algorithms. So we will be focusing on supervised, as you can see. Why? Because linear regression basically falls under supervised algorithms. Great. So first thing, let's talk about what supervised algorithms are and why do we call them. Okay, so just think of this scenario. Okay, that how can you teach a child that this thing is a tree? Okay, so what we do is we give them this image, okay, to the child, and we tell them that this is a tree. So after few iterations, they start recognizing it, that this thing is a tree. Great. So the same thing happens with these supervised machine learning algorithms. Okay, so what happens is we give them some data, like example the images, and we tell them that this image or this data is a tree. So we give them labeled data. Okay, so we give them the images. Example, in this data set we give them the images, and we attach these labels with the images, that what that image is, so that the algorithm will start recognizing it by training on it. Okay, so this is label. So what we call these things, these are labeled data sets. Great. Labeled data sets. So now let's move on. So let's talk specifically about supervised machine learning then. So in supervised machine learning, we have two kinds of tasks. Okay, so one is the regression task, and one is the classification. So these two are different because we deal with different kind of variables in this. Okay, uh, like example, regression task are where you predict continuous variables like temperature, and in classification we predict discrete variables like uh, example, I should just show you one. So example, I just gave them this image. I gave them this image and ask that is this a dog or a cat? So the answer can be either a dog or a cat. Okay, there can't be any other answer. It can't be a camel, it can't be a like horse or anything else. So this is discrete. Okay, this is discrete, where your actually the output is defined that what it can be. Okay, but in the case of these continuous variables, what we deal with are numbers. Okay, regular numbers. So example, if I ask you what is the temperature today, what is the temperature today, so what you will say is it's either 32.6 degrees Celsius outside, it's like maybe 30 degree or something. Okay, so it can't be a discrete value. So this is an example of continuous variables. Okay, as you can see, continuous variables. And same goes for your these like for numbers like money, for money and other stuff. Great. So now I would recommend you to just go through this text. So you can just pause here and just read it out. Great. So let's start. That what linear regression is. So let's get into that. So now linear regression. Great. So let's start with an example, a hypothetical example that what we own is an ice cream shop. Okay, we have this ice cream shop, and what we want to find out is that what our sale will be. Sale on Tuesday, on next Tuesday. It should be better. So on next Tuesday, what should be my sales? Okay, what should be my sales? Can I find that out? Can I predict it that what my sale would be on Tuesday, on the upcoming Tuesday? Well, we can do that. How? Because this is a regression problem as we are dealing with this continuous variable sale. Uh, okay, so now what we did was, okay, so the first starting point everywhere in machine learning and deep learning is data. Okay, so the first point is data. So let's collect the data. So we will just prepare this table for 50 days. Okay, for 50 days, each day we recorded the data in this table. So first one was for temperature and what our sale was. So I thought that maybe temperature is affecting my sales. So if I can model these two, if I can model the relationship between temperature and sale, so I would be able to predict that what my sale will be if I know the temperature on that day. Great. So since through these weather forecasting channels, we can predict that what the temperature would be, so that we can also predict the sale of uh, of our shop on that specific day. Great. So we recorded the data like 32 degrees Celsius when it was, then the sale was like $20,000, and when it was like 30 degrees Celsius, so it was a little less, 18K, and so on. So what we had was like 50 samples, okay, 50 samples in our this table. So what you can call this is a data set also. Okay, this is a data set, a very simple data set. Okay, and let's see that what do we have here in this data set. In this data set we have two columns. Okay, two columns. These both actually are variables. Okay, these both are variables, okay, that we will be dealing with. So now, but the difference is that temperature and sales are different kind of variables. So first thing is the sale is our target variable. Okay, sales is our target variable, and temperature is our what? A feature. A feature, or we also call them independent variables. Independent and target variable, or dependent variable, you can call it. Okay, so like this we have different variables in our data set. So now you can get it that why are we calling this a target variable? Because uh, we are going to predict this variable, the value of sale. Okay, our purpose is to predict the value of the sale. So this is our target variable that our model will be trying to predict. Okay, so we have to first define. Great. Now we have defined the data set and all that. So let's plot some sample data. Okay. Now comes the plotting part. So now I plotted this sales on y-axis and temperature on x-axis, and I just created a scatter plot. Okay. I just created a scatter plot. All the data points, I just plotted them here. So this is known as a 2D scatter plot. Great. So why is this known as a scatter plot? Because all the data points are scattered on the plot, like small dots. Okay, so that's why it's a scatter plot. Great. So if I ask you that, can you see any trend here? Can you see any trend in this data set? Yes, we can. And we can also show this trend by using the straight line, actually. The straight line, and it is totally showing us that what kind of trend is there. As temperature increases, we are seeing that we are having increase in sales. Okay, so this is a hypothetical example right now. Okay, so we are seeing a linear trend here, and a positive linear trend. As temperature increases, so the sale is also increasing. Great. Okay, now let's just come on to article again and connect the dots. Okay, so uh, one thing is that why are we calling this well, like a linear model? Why are we dealing with a linear model here? So there is a specific definition here. You can just check it out. Okay, just pause and check it out. Okay, and we will just discuss it later. Great. So now let's come here again. So this thing is also known as the best fit line. Okay, so this line is actually showing you the trend in your data set, or basically it's actually uh, showing the relationship between the sales and the sales and your temperature. Okay, now if we know the relationship that if uh, if like if my okay, so my example, this dollar is y, and whatever the temperature will be, it will be 2x of that example. Now if I have this, like example, I have temperature is 30 or something. Okay, if I have 30 degrees Celsius, so my sale for that, sale for when that day, where when my temperature was 30 degree, will be 2 multiply by 30. So that is example $60. Great. So this is a simple linear model. Okay, so how did we find this relationship using this best fit line? Okay, so let's move on to the equation for this linear regression model. So we can see it here. So first we will be starting with simple linear regression. Okay, so since we have only a single feature here, only a single feature, which is temperature, so we don't need any complex equation, complex algorithm. We can easily, by using simple linear regression, we can model the data set. Okay, so for that we have this specific equation for simple linear regression. Let's just write it down here and try to figure out that what it is. Okay, so we'll be starting with simple linear regression, so SLR. Great. And we have this model, or you can also call this your algorithm. Okay, great. So this is your basically H hypothesis, which takes theta. Okay, sorry, which is basically X, sorry, and it is beta naught plus beta 1 X. So this is our simple linear regression model. Great. So now what this model is, let's just talk about that. Great. So first, let's see that whatever this X is basically the input data, and this is our predicted value, and these two are basically the parameters, or you can also call them model parameters. They're the parameters of a model. Great. So now let's discuss a bit further. That specifically, let's discuss that what is this input data and how is it like coming here? How are we going to utilize this? Okay, so for that we would need some sample data set. Example, just zoom out a bit. Great. So we'll just need a sample data set. So we'll just create it here, X and Y. Okay, great, X and Y. And we have three rows here, one, one, two, two, and three, three. It's a very simple data set. Okay, it is a very simple data set. Let's plot it also here. So if you plot this, so we get something like this, 1, 1, 2, 2, and 3, 3. Okay, this is your Y and this is your X. Great. So now, so as you can assume that what is this input data? This input data is coming from your this feature column. Okay, this feature column. Okay, uh, and these two coefficients, specifically this beta naught, is also known as your intercept or bias. Okay, and this beta one is responsible for the slope coefficient. Okay, we will just see some examples. We will just see some examples and it will be totally clear. Okay, so just okay. So okay, yes. So the examples. Let's move on. So for this, actually, I'm gonna assign some value to these parameters. Like example, I will assume that. Okay, so just let's create a division here. And for over this model one, over this theta naught will be 0 and theta 1 will be 0.5. Okay, and this for model 2 we will have this theta naught uh, maybe like 0.5 and theta, okay, or just yes, let's just make it 0.5 and theta 1, let's keep it 0. Okay, great. So now we have two models here. So two linear models. Let's plot them. Okay, so we have over this plot here 1, 1, 2, 2, and 3, 3. Great. Let's just create the plot. Okay. Now, so as you can see, this axis is showing me the x, and this axis is showing me the y. So now, here there is one important thing that our actual data points, our actual y, is known as your y normal yi, and the predicted value that our model will be predicting is known as y hat. Okay, y hat. So what will be the y hat for the first data point? So just keep it like this. So for the first data point where our x is 1, okay, and our theta naught is 0, and our theta 1 is 0.5, multiply by what? 1. by what? By this specific equation, as you can see. Yes, by this equation, we are predicting the value for y. Okay, so what is the y hat 1? Y hat 1. So it is, as you can see, 0.5. Yes. And what about for the second data point? It will be just the half of it, as you can compute it. Yes. So it will be it will be 1, and for this it will be 1.5. Great. So let's print. Let's just plot it. So I will just plot it using red. So our first y hat will be 0.5. So somewhere here, so this is y hat 1. Great. And what about for the second? It's here y hat 2, the second predicted value. Okay. And what about the y hat 3? It's 1.5. Okay. So it's somewhere here. So it's y hat 3. So this is the line. This is the model. This is the model. Okay. Now, if I would ask you that, is it showing the correct relationship between our these actual values, these three axes, and so is it showing the right trend in our data set? No, totally no. Because as you can see here, we are having some error, okay, between our actual value and the predicted value. We have some gap. We have some gap. We have some distance. You can say it delta D. Yes, delta D or our error. So that's why this is not the correct model that is showing the relationship exactly. Okay. So let's see that is this model 2 better? Let's try to just plot it. So I would recommend you to first plot it on your own. It would be great. Uh, so again, so I will be using the same plot. Okay. So for this first, let's compute the values. So for h1, we have this 0.5 plus 0 multiplied by 1 equals 0.5. Yes. And same goes for your h2, h3. Okay, for basically the second and third values also 0.5 and 0.5. Okay, so we'll just plot this here. Uh, for this, we have 0.5 here, so it's actually intercepting. So I will just draw a triangle for our model 2. Okay, so a triangle for our model 2 here, here, okay, and just here. So if you'll see this, so our sorry, yes, model 2 is something like this. So this is our model 2. So what do you think that which model is better? Which model is better predicting uh, the trend in our data set? Who has the least error? You can say the least distance from the actual values. If you will see, this model 2 is actually having a huge distance from the actual values. So that means that our model 1 is better than model 2. Okay, but it's not the best. So we can't say that this is the best fit line. Okay, we can't say that this is a best fit line because it's not fitting best in a model. We can have a better line, which can be something like this, just overlapping through our data points, something like this. In the simple data set now, we can have the situation where our this model will overlap all the actual data points. Okay, so how can it be? We can have model 3, okay, uh, whose theta naught should be like something 0, and theta 1 should be 1. If it's the case, so you can see that h1 will be 1, h2 will be 2, and for the third data point, it will be 3. Okay, so it will be totally overlapping all the data points. Okay, so you can say this model is the best fit model or the line. Totally great. So normally this doesn't happen, and actually, just let's consider an actual real world scenario where you will be having like a sort of 10 million data points. Okay, you'll be having 10 million data points. It can be the data coming from an e-commerce store or anywhere else. Okay, and you will have to find the relationship, the linear relationship. So at that point of time, you can just assume that optimum what the optimum parameters will be. Okay, you can't just wing it. Okay, you can't just randomly pick any values and assign them to our theta values. So okay, so maybe actually I have used theta instead of beta. Okay, so they can be like interchanged. You can either use beta naught instead of theta 1, theta naught, not a problem. Okay, so now uh, optimum parameters, yeah. So to find this out, we actually have few algorithms. So for that, let's move on to the content again. So yes, we have these optimization algorithms. First, let's discuss about that, what optimization is. So as you can see, optimization refers to the task of maximizing or minimizing a function. Okay, so in our current scenario, what we want to do is we want to minimize what we want to minimize the cost or the loss function j. So first, let's discuss about that. What is this cost function? What is this cost function? Yes. So let's just discuss about that. So the cost. Okay, like example here in this case, you saw that our model was having some basically our predicted values, like example this y hat 3 and y3, our actual value and predicted value, were having some distance between them. So this is the error. Okay, and if you sum all the errors now, if you sum for y hat 2 and y2 and for y hat 1 and y1, all these errors, so you will get the total error of the model. Okay, the total error of the model, and that is the cost. Okay, so that is the cost. And how can we estimate this cost? Let's see how can we do that. So just I will just draw a random random model here. Okay, so 1 1 2 2 and 3 3, and what we have is this model where we have this, where we have these predicted values 0 0.5 0 0.5 and 0 0.5. Okay, we have something like this. This is our model, and these are our actual data sets, the same one that we just worked on. So now how can you estimate the cost? So let's just take the distance between the actual and the predicted. Okay, all of them. So now this was 1 2 3, 1 2 3. Okay, now so when our this our x was 1, so what was the actual value? What was the actual value? It was 1. So I'm just say it like this. So y1 minus y hat 1. What is it? So it's 1, and this one is 0.5. Okay, so 0.5. Yeah, so it means 1 minus 0.5, that is 0.5. That is actually the error. Yeah, error in the distance, or the distance, you can say. Great. So now what we want to do is we want to find out the total error of the model. So what we'll do is we'll use this sort of a formula. So just we will sum them up. Okay, sum them up. So for we will just take this, and then y2 minus y hat 2. Okay, and then y3 minus y hat 3. Okay, so so this was 0.5 plus y2 minus y hat 2. That means 2 minus 0.5, that is 1.5. Then plus y3 minus y hat 3, that means 3 minus 0.5, that is 2.5. Yes. So what will be the error? So it will be around like what? Uh, 4.5. Yeah, 4.5 is our error. So normally this you can say that this can work, but normally in machine learning what we have is a different uh, like a different formula for this. So what happens is what happens if your this y hat 2 was like above it, above the actual value, so these will just cancel up. Okay, these will cancel up the values. So that's why what we will do is we will just take the square of all these, so that actually the problem of these what you can say uh, these signs, negative and positive signs, will just go. Okay, it will just go away. uh, so by this we did that, so we can just write the formula. So it is yi minus yi hat square, whole square, and from where to where? I is equals to 1, from I equals to 1 till m. So I told you maybe the m was total number of rows. Yes, here it was 3. Totally great. So this is your uh, sum of all the errors, sum of squared errors. So it is also known as SSE. So this is an important formula, okay, that is used in many other algorithms while optimizing them. So SSE, sum of squared errors. Okay, sum of squared errors. You can just write it down. Great. So now, how this cost function derived? So this cost is just derived from SSE, but we have normalized it using just by adding few things. Okay. So for cost function, what we have is, for cost function J, what we have is something like this. Okay, cost function. So that is J, which takes theta. Okay, and it is 1 by 2 m summation of basically here the same as C, y I minus y hat I. Okay, square, whole square. So this is your cost function. So what we want to do is we want to minimize this thing. Okay, so we will pick those theta naught and theta 1 which will minimize this cost. Okay, so we want that sort of a model which will have the least distance from the actual values. Okay, so that's important thing. Now how can we find those out? How can we find these optimum theta naught and theta 1 values? So for that we have optimization algorithms for just like a very simple algorithm, you can say, but this works with simple data sets, really simple data sets. But if you have like many columns, like thousands of columns in your data set, so this won't be feasible. Totally not feasible. This first one, okay, it won't be feasible. So the first one is ordinary least square estimator, and this can work in many scenarios, in many general scenarios. Okay, so it is also known as OLS estimator. So we will first see that, how can we use OLS estimator, uh, and let's also see the second one. So this one is gradient descent, which is the most important algorithm of machine learning. So this is used to optimize, you can say, like every algorithm which is out there. So this is the most used optimization algorithm in machine learning and deep learning both, gradient descent. Great. So first, let's talk about OLS. So for OLS, we have a one short thing. You can find the optimum parameters by just plugging values in the function. Uh, okay, in the function. So we have a formula here. So in order to find your theta one or beta one, you can say, we have this formula where we have this your xi minus x mean multiplied by yi minus y mean, okay, divided by xi minus x mean ka whole square. Great. So you can, if you want to write it using numpy, so there is a great implementation below also. So in numpy, this will be actually x, this will be a numpy array, np array. Okay, it will be a numpy array, and you will be just like subtracting all the values by their mean, the mean of the array. So x dot mean. Great, we got the first part. Okay, now we have to multiply it with this, so we can say y minus y dot mean. Y is also a numpy array. Okay, a numpy array, and divide by your x minus x dot mean whole square is, so double star 2. So that is it. And or we have to just take the summation of these, so you can just use np dot sum for that, np dot sum, in order to uh, get the sum of the array. Okay, sum of the resultant array. So through that, we will be able to find out the theta 1. And for theta naught, we have first, we have to find the theta 1 value, and we can just plug it in here and use the mean of our y and x arrays. Okay, and we will get the theta naught value. Okay, so that's it for now. And if you like the video, so just let us know in the comments, so that we can bring out more of these amazing videos and totally like help everyone out. And so that would be great. Okay, thanks a lot, guys, and please like and share this.